We also talked about the motion of a pendulum and how that exactly corresponds to simple harmonic motion. And so we said that we have a pendulum here, for example, of length L and some kind of mass that's hanging from it. And if you let it swing, we'll measure theta from the vertical. Okay. If you let it swing, the question is it exactly experiencing simple harmonic motion? And the answer is yes, as long as theta is not too big. Okay, and so whenever we're talking about pendula that are exhibiting this behavior, we're talking about thetas that end up being a bit less than 15 degrees and down. Okay, and I'll get to that again in a second as to why that is. But part of what is going on with simple harmonic motion is that there is a restoring force. There is some force that is bringing this object back. It goes up, it comes back, it goes up, it comes back, it goes up, it comes back, etc., etc. There's some force that looks like a Hooke's law force that will be doing that. So the question we have to ask is, what is that force? If we draw a free body diagram for this object right here, we know that there's the gravitational force going down, and there's the tension force that's directed along this way. Okay? And so, breaking this up into components, we realize that the tension and this component of the gravity are balancing each other out. And the restoring force is this component of the gravity right here, the gravitational force, this component of the gravitational force. If this angle is theta, which it is by geometry since that matches this angle right here, and we're looking at this is our new y, and this is our new x, we want this x component of the gravitational force as the restoring force. So F restoring is equal to, since it's going to the left, we're going to call it negative, is equal to negative mg sine of theta. Okay. And to put things in terms of a Hooke's law sort of force, remember that a Hooke's law sort of force would be F equals minus kx. We need some constant times some linear quantity. Okay? And this isn't exactly that, so we're going to put this in terms of arc length instead of in terms of theta, so that theta, well, if you remember from last semester, S is equal to the radius times theta. The radius of our circle is just going to be the length of this string. So S equals L times theta, or theta equals S over L. So we can put this in as minus mg sine of S over L. So this is close to looking like a Hooke's law force, but not exactly. And so what we can do with this is realize that for small arguments right here, okay, for about 15 degrees and lower, the sign of this argument is just equal to its argument. Okay? So, let me write that down here. For small psi, I used that in class, sine of psi is approximately equal to psi. Okay? That's a mathematical fact. You can check that on your calculator for small angles, that this does actually end up working out. And so what that means is that then for small angles, we can write this restoring force as minus mg times S over L. So now we do have a sort of Hooke's law force, and not any sort of Hooke's law force, we have a Hooke's law force, where it is definitely a restoring force of minus mg over L times S. Okay? So, why is this important? This means that now we can make some direct analogous relationships between a Hooke's law force and the force we just found for a pendulum. F equals minus mg over L times S. This tells us that an effective K is mg over L. So this is analogous to this. They map onto each other in that case, and likewise the X maps onto the S, the arc length. So K is then equal to mg over L, and we know that omega is equal to the square root of k over m, okay, or that the period is equal to period is equal to 1 over the frequency, and frequency is equal to omega over 2 pi. And so putting these things together, we realize that t is equal to 2 pi over omega, so t is equal to 2 pi square root of m over k. And so over here we have an m, we have a k, so you may as well solve for m over k. So bringing this over there, L over g is equal to m over k. So what this tells us is that the period for a pendulum is equal to 2 pi square root of L over g. So the period of a pendulum that is not swinging at a very steep angle, but is at one of those smaller angles, the period doesn't depend on the mass of the object at the bottom of the pendulum. It depends on the length of the string and the gravitational acceleration of the Earth at that point. Okay? And like I mentioned in class, geologists actually use this idea, or you can use it, to try to tell if there's something different about the ground below you. Like there might be some kind of deposit below you, some kind of either vast amount of water, some kind of ore, some kind of oil, something different. Okay? It would be a hint as to that there might be something there if you have a string of specified length, like I can measure this, know exactly how long this is, and then also time, how long it takes to go through one period. That would be the t. So then, with that, I can measure g, and I can see exactly how much g deviates from other places, and be able to look at that and say, okay, the ground below me must be less dense than other regions, and therefore there must be stuff there that contributes to that, or the ground is more dense than other regions, which would give us a stronger gravitational pull in that specific spot. It would be a very slight difference, but it would still be a difference that you could tell. So, but this is another relationship that we got at by realizing how this pendulum motion is similar to the motion of a spring. Just looking at this idea of simple harmonic motion and realizing how these different concepts that are seemingly different are actually related because of their periodic motion and their specific restoring forces.